blood vessel in diameter?
Good. Blood thickness is the viscosity. I can't change my viscosity in the next 5 minutes, quite likely. My vessel length is something that's going to be hard to change as well in the next 5 minutes. But the diameter, you're right. That vasomotor center in your medulla can change the vessel diameter, and it can change it rather quickly. So what we can do is that vasomotor center connects to our blood vessels, and that vasomotor center can either tell those vessels to constrict, which is called vasoconstriction. That in turn will decrease the diameter of the blood vessel. This is just like the operation of a hose. If you all of a sudden constrict your hose, what happens to the pressure behind that blood? You've got to increase it, right? Because to get that blood to flow through the same vessel, but yet with a smaller diameter, we're going to increase the blood pressure behind that blood. Likewise, if you need to decrease your blood vessels, that vasomotor center will send less stimulation to our blood vessels. That smooth muscle in the walls of those vessels will relax, promoting vaso what?
Relaxation.
Dilation. Good. So your brain, using that vasomotor center in your medulla oblongata, can actually constrict vessels, increasing blood pressure, or relax vessels and decrease blood pressure. Certain activities that you do actually can either increase or decrease. We're going to talk about hormones and chemicals that your body naturally releases that either will vasoconstrict or vasodilate. Did you know that listening to your favorite song has a dilatory effect on your blood vessels? Get in the car, crank up your favorite music, you will actually get your blood pressure to drop relaxing listening to your favorite music. Makes sense, right? Because you're kind of in the mood of listening to whatever it is that turns you on, I guess you might say. Okay, so here's, do you have a question? Okay. Here's a couple of ways we can actually modify vessel constriction or vasodilation, and it's based on a couple of input devices. Back in Bio 210, you might have heard very briefly about types of receptors in our body. And one of those receptors is called a baroreceptor. Baro is like a barometer, and it's detecting pressure in those vessels. Another type of receptor is called a chemoreceptor, and it's detecting chemical composition of your blood. Finally, you yourself can control your blood pressure simply through your emotions. If you get excited and wound up about something, that can of course increase your blood pressure. But if you're just at home relaxing, listening to some music, enjoying just not doing anything, then that can also decrease your blood pressure. So your mental state of being is one other mode of fashion for kind of controlling vessel diameter and blood pressure. All right, let's talk baroreceptors for just a moment. Think back to the chart we just covered. We had the highest pressure in the aorta, it dropped off steadily in the arterioles, continued to drop in the capillaries, and by the time you got into the vena cava, we were pretty much at zero pressure. So, if we're wanting to monitor pressure in your body, where should we stick these pressure monitors?
Aorta.
Aorta, exactly. Why would you not want to put these pressure receptors in your vena cava? There's not hardly any pressure there, you're right. So you're not going to get a whole lot of information from the vena cava. You're right, this is exactly where our body puts these pressure receptors. These baroreceptors are detecting blood pressure. You'll notice that there are some of them in the aorta, coming off the heart, and then come across here, you'll notice they're also in the carotid arteries. Where do the carotid arteries take blood? To the head. Do they travel up in your neck and go to your brain? So of course those carotid arteries are a place that we want to monitor pressure as well. Because if not enough blood gets to your brain, what happens to your brain? Stroke. Yeah, so we got to make sure we get that blood up here to the brain. Alright, so you actually have these pressure receptors called baroreceptors. They are sensory receptors that tell your medulla oblongata what's going on. Why the medulla?
It controls breathing and heart rate.
Controls breathing and heart rate, good. If we can take that information into the medulla, which is a cardiovascular and a respiratory center, the medulla might say, pressure's too high. Instead of going back to the heart with the control to the vessels, notice where that control goes back to. It goes back to this little thing right here in the right atrium. What is that thing? SA node. What will we now do to that SA node? Slow it down, right? If you slow down the heart rate, what happens to your blood pressure and cardiac output? Decreases. Yes, drops it. So, in addition to that, notice where else we go. We go over to an arteriole. We take that vessel diameter and do what? Dilate it. Relax it. So if your blood pressure is too high, what your vasomotor center does is it says, okay, pressure is too high, you can have a blowout here. Slow down the heart rate by telling the SA node to slow things down. I also tell those blood vessels to vasodilate, relax and open up. What does that do for the resistance? It decreases it. It makes it easier for blood to flow through those blood vessels, and in turn that's going to lower your blood pressure. So this is a way to kind of afford a control mechanism, a short-term control mechanism over our blood pressure by altering heart rate and by altering our constriction or dilation of our vessels, which in turn controls blood pressure. Complicated mess, isn't it? A lot going on here. So really important for that vasomotor center to control what's going on, because it can accommodate for changes in blood pressure over the short term. Alright, so I've got you a blank there in your worksheet under the first bullet point. It says that increased blood pressure stretches baroreceptors. These are afferent nerves that carry information to the VC. Boy, let's translate that into plain English. What is an afferent nerve? It's a sensory, good. It carries info to your central nervous system. Okay, so afferent means sensory. What does VC stand for? Vasomotor control, yes. So that vasomotor center is located where? In the medulla, good. Alright, so notice we've got an increase in blood pressure. That means there's more stretch in this aorta and in that carotid artery. The sensory information goes to your vasomotor center. Next it says this will lead to a decrease in sympathetic stimulation of the arterioles. Sympathetic stimulation, what does that mean? What's usually involved?
Relaxation.
Yep.
Epinephrine, right. So if we decrease the flow of epinephrine to these vessels, then that's how we get them to vasodilate, relax and open up. Okay, so the next blank there, vasodilation is achieved. We also decrease the heart rate, and we also decrease the blood pressure. This sounds just like what type of feedback mechanism?
Negative.
Negative, yeah. So it's a negative feedback to control the blood pressure and restore it back down to a normal level. So how will vasodilation affect blood pressure? What do you think? Decrease it, yeah.
If you couldn't decrease your blood pressure, like what would happen? You'd like bust an artery or vein or something?
It would probably cause an aneurysm where you'd have a weakness in the blood vessel and it would blow out, yeah.
Just lead into your body?
Yeah, it'd be hemorrhage, an internal hemorrhage, yeah. Or worse, it'd be in the brain or something of that sort. Julie?
Isn't it sending anything out to cause the dilation?
Right. We're just inhibiting, we're just, instead of doing something active, we're kind of reining things in, exactly. Alright. Let's take the flip side. Let's say that you're laying down. Okay, when you're laying down, these vessels tend to open up, vasodilation. All of a sudden, somebody says, come quick, come look. So you hop up and stand up really quickly. In order to get that blood pumped up to your head, now what do we have to do? Vasoconstrict. So if you're laying down and you've got low blood pressure and you suddenly stand, this vasomotor center now tells your SA node to do what? Speed it up, get it faster, right? Increase the heart rate. It tells the arteriole to constrict. Both of those activities together do what to your blood pressure? Increase it, because you've dealt with the peripheral resistance issue and you've dealt with the issue of speeding up the heart rate to deal with the cardiac output issue. So that's what the vasomotor center does if you happen to have low blood pressure and you need to increase that blood pressure. we speed up the SA nodes firing, and we also constrict our vessels, specifically those arterioles. All right, so vasoconstriction, your next little bullet point there. And how will vasoconstriction affect blood pressure? Increases it, good. All right, so changes in pressure trigger that VC center, that vasomotor center in the medulla, to either increase sympathetic stimulation to the heart and to blood vessels, or it decreases stimulation to heart and to blood vessels. So if you're thinking here in terms of epinephrine, you're on the right track, because that's what the sympathetic nervous system operates with. So you see that epinephrine not only tells that SA node to fire more quickly and it increases the activity of the heart, but you can see that also we're dealing with the activities of the blood vessels. So if somebody takes a beta blocker, what are we blocking? Epinephrine. And you can see that we're not only affecting the activities of the heart, but we're also affecting the activities of the blood vessels. So you're not only slowing down heart rate using a beta blocker, but you're right, you're vasodilating, you're opening up those blood vessels as well. So beta blockers actually have a dual effect here, affecting not only heart rate, but also the constriction of those vessels.
You told us that AMP was an antagonist to epinephrine?
AMP is an antagonist to aldosterone.
Aldosterone.
Aldosterone, yeah.
Okay.
Which we're going to come to that on the next
I'm
yeah.
sorry.
That's all right. All right, you have questions, Julie?
Serotonin is a vasoconstrictor too, right?
Yes, because it's the blood clotting effect, yeah.
But is it only work when you're bleeding, or does it play a role in all this too?
I think it plays a minor role. We don't usually talk about it in here and its role in vasoconstriction, but you're right, especially with blood clotting it's an issue, but it's probably a minor player to the epinephrine. Let's talk chemical control. Okay, so we've got chemoreceptors that are shown next to the worksheet. The feedback mechanism is the same. Those chemoreceptors send information to the vasomotor center. In turn, the vasomotor center will either increase sympathetic stimulation to the heart and vessels, or it will decrease stimulation. So the routine here with baroreceptors and chemoreceptors is the exact same routine. The outcome, of course, depends on the input information. All right, so let's take a look. If you read there under chemoreceptors, it says we are looking for sensitivity levels to oxygen, carbon dioxide, and pH. Boy, this is taking a step back, isn't it? This is going back to Bio 210 again. What is the normal blood pH? 4. Very narrow range, alkaline pH, okay? So if we decrease that pH, we are going into what? Acidosis, right. Going down is acidic, and we say that we're going into acidosis. And acidosis is related to the amount of carbon dioxide you have in your bloodstream. The more carbon dioxide